Questions about anything from last time? About anything? Well, today's a fun lesson about the residue theorem, which is one of the sort of highlights of the course and one of the most useful tools that you'll get of a course on complex analysis. And it's about calculating an integral and kind of reducing an integral to algebra. And the famous theorem is the residue theorem. It's about integrating around a closed so gamma is a simple closed contour. Should have mentioned that. Gamma is a simple, meaning it doesn't cross itself, closed curve. And I've got a function f that's analytic inside and on gamma. That means there's a bigger open set containing the whole thing, including the inside of gamma. And so f is analytic except for finitely many isolated singularities inside gamma. Okay, so, and I'm calling those A1 through A capital N. Then this integral around gamma of f is a finite sum. It's 2 pi I times the sum of the residues of f inside gamma. So that would be the sum of the residues at the a ends of f. And remember, the residue of f is the -1 term in the Laurent expansion. And especially if those are poles, which very often they are in the case where this is applied, it's just a matter of messing around with power series to determine that magic number, the residue. Okay, that's it. And at the end of the hour last time, I indicated how you'd come to understand this thing. So let's see, let me just copy this. So the demonstration of this thing is, let's say I just have a few of these things. I'll make 4 of them, of points like this. And so the proof would, I know a baby residue theorem about little circles. So if I had a bunch of little circles that were around these A's, so there's a little circle around A1, they need to be small enough that they don't overlap. And let's see, I want these circles to go clockwise. And then the observation is that I can split this thing into 2 curves. Let's see, I'm going to take cuts here. On the top half, I'm going to go to the right. On the bottom half, I'm going to go left. And if I connect these disks like this, then I get a top half that's going counterclockwise, and a bottom half that's also going counterclockwise. And finally, I connect to this side. Okay, and so when I add up those 2 halves, the top half and the bottom half, the little purple line segments cancel because they're going opposite directions. And I get the blue, the gamma is a counterclockwise curve, and the green ones are clockwise. Yeah.
Can you clarify the notation used in the integral for the residue AN F?
Yeah.
Like the residue of AN times F?
No, it's the residue at AN of F. That's the A-1 term in the Laurent expansion. I defined that last lecture.
Could you add parentheses to it? to the residue?
You could if you like.
Wait, no. Right.
So you mean you would rather I had parentheses around the F?
Okay. Yeah, that makes more sense.
But then I'd have to do that consistently, it's a custom not to do that. Does the book do that?
Not particularly.
Yeah. Okay. Yeah. It's a kind of a custom. That's a sub AN there. So.
It just helps me understand.
Yeah. Okay. So let's see if I write this out now. Notice that the top half is a simple closed curve. And so we have the Cauchy theorem on the top half. So I'll call that gamma sub top plus the integral along gamma sub bottom. Those are both counterclockwise simple closed curves. And F is analytic and inside and on those things. Because we punched out the places where F was singular. So these are both zero by Cauchy's theorem. And when we look at it, we realize the purple cuts cancel each other, and this boils down to the integral around gamma, the outside one, counterclockwise. And then we have a sum of the green ones clockwise. So that would be plus sum, as n goes from 1 to capital N, of the integral around what I would call, if I do the counterclockwise circles, minus the circle of radius something small, epsilon n about an of f dz. And remember that's going to spit out, this is going to spit out minus the clockwise version of that. So a small epsilon radius about an. So this is a clockwise circle. No, this is counterclockwise. Sorry. And that's the thing that the baby residue theorem. That integral is 2 pi I times the residue. So this one is equal to minus 2 pi I times the residue at the center of F. And so when I put those on the other side, I get the residue theorem. Questions about that? That's how you see it. Let me do some fun. Starting now, I'm going to do a couple days of fun applications of this thing. I'll start with a biggie. A very famous integral in the subject, actually in engineering and science and math. You probably saw the Laplace transform in your ODE class. There's another one called the Fourier transform. Which is given a function on the real line from minus infinity to infinity, you get a new function called f hat of s. And sometimes there's just 1 over 2 pi or something in front of this integral, but I'll get rid of that 1 over 2 pi. Let's see, so I have a function of x, and I integrated against e to the minus I sx. And that spits out a new function, f hat of s, for all real values s. So I take a function on the real line, and it spits out a function on the real line. It turns out to be a very important thing. And so a big fact is that the Fourier transform turns differentiation into multiplication by something. So let's see, if I take the Fourier transform of f prime, that turns out to be minus I times s times the Fourier transform of f. So it turns differentiation into multiplication by minus I times s. And you could see that by doing integration by parts when you calculate that integral. And if you do it twice, for example, f double prime, this is why it gets used in partial differential equations, you get two minus i's, and so it becomes minus s squared times f hat of s. What? I times I is minus 1. Yeah, the minus...
But isn't there a minus initially?
Minus 1 times minus 1 is plus 1, and then the I times I is minus 1. Yeah. Okay, so the Fourier transform has an exciting feature that it takes differential equations and sends them to algebra equations. Okay, it takes differential equations and turns them into algebra. Well, that wouldn't be a big deal because, so what? So this would turn a differential equation into algebra equation, which you could solve for f hat. And that wouldn't be a big deal unless it's a routine thing to get f back from f hat. And so another even bigger fact, it's easy to undo the Fourier transform. Can undo the Fourier transform. And the famous formula is f of x. I guess I have to put the 1 over 2 pi back here. Is 1 over 2 pi times the integral from minus infinity to infinity. It looks just like the Fourier transform. The only difference is it's an e to the plus is x. And now I'm integrating with respect to s. So it looks like I just do Fourier transform twice and I get f back. And that's kind of the way it is. But the annoying thing is that when you do the inverse transform, it's a plus e to the I plus isx. I'm not going to do demonstrate the Fourier transform facts, but I'm going to show you that now we can use the Fourier transform to calculate. I can calculate a famous Fourier transform using the residue theorem. Let's calculate let's see, this is the Fourier transform. I'm going to make my life easier and take an e to the I plus sx over x squared plus 1 dx from minus infinity to infinity. That's, let's see, what is that? That's f hat at minus s for f of x equals 1 over x squared plus 1. And I want to calculate this when s is positive. Well, let's see. So these things are very often applications of the residue theorem, and one of the most common contours to apply the residue theorem is this big D in the upper half plane. So let's see, there's 0 is here. Let's make this be a minus big radius and a plus big radius along the real line. And this thing's going to go around counterclockwise. And notice that function, let's see, I'm going to take here a complex function, f of z. I shouldn't have called, maybe I should call this g over here since I'm going to have an f. G hat, where g is that. But my f here is going to be e to the I s z over z squared plus 1. Pretty much the thing inside the integral. That has a single bad spot inside that d, namely at plus and minus I. Well, minus I is outside, but plus I is inside. So, in fact, that's going to turn out to be a pole. And so there's a single spot where there's an isolated singularity. And I'm going to call this circular part C sub r. And I'm going to call this line part L. Let's first think about the line part. Okay, the line part integral along L of f of z dz. I parameterize L by z of t equals t, as t goes from minus r to plus r. And let's see, z prime of t then would just be 1. So that would be the integral from minus r to plus r of e to the I s t over t squared plus 1 dt times 1 dt. Z prime of t is 1. And e to the I st is cosine st. So that's equal to integral from minus r to r of cosine st over t squared plus 1 dt, plus I times the integral from minus r to r of sine st over t squared plus 1 dt. Let's see, sine is odd, and t squared plus 1 is even. So that's an odd function divided by an even function. This is odd. And this one is even. Cosine is even, and t squared plus 1 is even. So this is even. So in fact, this integral along the line part is just going to be equal to, this odd thing around a symmetric interval is 0. I don't have to even think about it. That's equal to a big fat 0. So this integral is 2 times the integral from 0 to r of cosine st over t squared plus 1. So we're going to calculate that real integral. That's the thing we want. Okay, the residue theorem is going to tell us that the integral around that gamma, did I call it gamma? I'll call that whole thing gamma. the integral around that whole thing, gamma, of f dz is 2 pi I times the residue at I of f. This is what we want, this integral along L. We want as r goes to infinity. That's going to be the thing we want. Actually, yeah. Okay, so the most important thing, I claim that the integral of f around the circular part tends to 0. So around the circular part, f dz, that's going to go to 0. And so I'll have the integral along the line part, that's what I want, plus the integral around the circular part, that goes to 0. That's going to be equal to that number. It's going to be easy to calculate. And so as I let r go to infinity, that number on the right is my answer. Okay, so let's see why. There's two steps here. One, e to the ISZ is bounded by 1 in the upper half plane. Upper half plane. So I'll always use this notation for the upper half plane. Let's think about that. Here's why. Let's see. E to the I s times x plus iy. Take the modulus. Let's see, that would be e to the I sx times e to the minus I squared is minus 1, so that'd be minus sy. This has the first thing has modulus 1. And the second thing has modulus, it's a real number, so of course it's a positive real number, and so this modulus is just itself e to the minus sy. So that modulus is e to the minus sy. And if s and y are positive, that's less than 1. So that's, in particular, it's less than 1, which is e to the 0. Because the exponential is a strictly increasing function. When y is positive, or actually greater than or equal to 0 too, I'll make it less than or equal to. So it's less than or equal to 1 in modulus when y is greater than or equal to 0. That's the upper half plane. And that's because the s was positive. If s were negative, I'd be sunk right at this point and have to think about something. Okay, so that thing's bounded. And now I claim that the thing in the denominator, I've got a 1 over z squared plus 1 in the denominator. So I want the denominator estimate that I used when I did the fundamental theorem of algebra, for example. So the denominator estimate, the z squared plus 1, is greater than or equal to modulus z squared minus modulus 1. Okay, and now let's think about if that radius was something big on C sub r. This would be greater than or equal to r squared minus 1. And if that was a big radius, of course, that would be the real number, r squared minus 1. So this would be equal to r squared minus 1 when r is big, in particular when r is bigger than 1. So I get the basic estimate that e to the I s z over z squared plus 1 would be less than or equal to, the top thing is bounded by 1, and the bottom thing is greater than or equal to r squared minus 1. Okay, so that's true on C sub r when r is bigger than 1. So in particular, using the basic integral estimate, which is going to be used daily now. So the basic integral estimate will tell me that the integral around C sub r of e to the I s z over z squared plus 1 dz is less than or equal to the max of that function on C sub r times the length of that curve. Okay, so, and the max is less than or equal to 1 over r squared minus 1. And the length, it's a half a circle. So instead of being 2 pi r, it's just pi times r. And that goes to 0. Let's see, we need r to be bigger than 1 for that. And that goes to 0 as r goes to infinity. And that's what I claimed. Okay. So we're almost done. The last step is to calculate the residue. And that's fairly easy here because, let's see, I can factor that denominator. That makes it kind of straightforward. So let's see, e to the I s z over z squared plus 1. I factor the denominator and get 1 over z minus I times z plus I. And if I want the Laurent expansion, I can play around with series and get it. Let's see. Here's how you do it. I pull out the 1 over z minus I. And what's left is something nice and analytic inside and on the everywhere. So this thing is analytic near I. And therefore it has a power series expansion. I like to use capital letters for this one. A naught plus A1 times z minus I plus A2 times z minus I squared plus dot dot dot. And now when I distribute that 1 over z minus I through, I would get an A naught over z minus I, and then the regular power series, plus A1 plus A2 times z minus I, plus etc. So this is a convergent regular power series. And this thing in the front is the principal part. It's the whole principal part. And in fact, it's only the residue term. Remember, the residue term is the coefficient in the negative power expansion, in the Laurent expansion. So that's the residue of I of f. So I calculated it just by playing with power series. And that's the A naught term in a power series for that analytic function. And the A naught term by Taylor's formula spits out that A naught is equal to, this is the function that it's the power series for, and A naught would be evaluated at z equals I. And that's an easy thing to get. That would be e to the is times I over I plus I. That's equal to e to the minus s over 2I. So I'm done. Almost, I guess. I have the integral along L plus the integral along C sub r of f dz is 2 pi I times the residue at I of f. This one goes to the integral I want, namely the integral from minus infinity to infinity of e to the is x, or I guess I would use t when I parameterize it, e to the ist over t squared plus 1 dt. That's the Fourier transform that I want. This one tends to 0. And this I just calculated is 2 pi I times e to the minus s over 2I. And so sure enough, this thing we realized is 2 times the integral from 0 to infinity of cosine st over t squared plus 1 dt. And so it's no surprise that, yeah, that's a real number. It's the 2's cancel. It's something beautiful. It's namely pi e to the minus s. And that turns out to work when s is positive. If s is 0, you can just calculate that integral. It's the arctangent function. It would be easy to calculate. And it would just be pi, in fact. But you might ask yourself, what do you do if s is negative? Well, then that thing would be bounded in the lower half plane in the numerator. And so, in fact, if s is negative, you take a d that goes down. Let's see, and that would make it clockwise. So I'd have here minus r to plus r. Go here. And then I'd have a singularity at minus I. And then e to the ist would be bounded in the lower half plane. E to the ist less than or equal to 1 in the lower half plane. And I could do the same thing and get a similar formula in the negative s case. But then I'd have to, that's a clockwise thing, so the residue theorem would be I'd have to make sure that I'd have a minus 2 pi I times the residue at minus I of the f of z, because it's clockwise. I won't do that calculation, but it's kind of fun. Well, that's doing that routine above. We'll do it a number of times, and you'll see it kind of spits out the same thing every time. So I'll tell you an important formula to keep in mind. that calculation we did can be done more generally. Let's suppose F and G are analytic near a point on, say, a disk of radius r about A, and G has a simple zero at A, meaning a zero of order 1. Let's see, a simple zero at A means that G of A is 0, but G prime of A is not 0. That's a zero of order 1. That's what it means to be a simple zero. Then the important formula is the residue at A of F over G is F of A over G prime of A. And the y is a very simple thing. Let's see. We've done this before when we were studying the zeros of analytic functions. So I'd have G of Z has a power series expansion. A naught plus A1 Z minus A plus etc. And remember when we were studying zeros, this is the A naught is the value. A naught is G of A. So that's 0. And A1, by Taylor's formula, is G prime of A over 1 factorial. And that's not equal to 0. And so G has a series expansion that starts with a A1 term. And remember what we did, we factored out Z minus A from this, and we got a power series with this same radius of convergence. So I pull out the Z minus A1, minus A, and I get this, A1 plus A2 Z minus A plus etc. This is what I called capital G of Z. And that has the same radius of convergence as the little g series. And so it's an analytic function. That's analytic. And notice that G at A is A1, and that was equal to G prime of A. Okay, so now my function, that was F of Z over G of Z, and that's equal to F of Z over Z minus A times capital G of Z. And just like I did in my example there, when I factored out the Z minus I can pull out that in front, and what's left is a nice analytic function that has a power series. Okay, and so I can expand that in a power series. Here's where I like to use capital letters. A naught plus A1 times Z minus A plus etc. And then when I distribute that, through, I get the residue term staring me in the face, just like I did in my example, and the rest is a regular power series. So this junk here converges to something analytic. Near A. And this is the residue term. And so the residue term of f over g is a naught, and that's the value of f of z over g of z at z equals a. Of course, that's f of a on top, but we noted above that the g at capital G at a is the little g prime of a from the Taylor expansion. And so check. That's all there is to it. That simplifies that calculation. So now I don't have to do this power series game again. I don't think the book makes a big enough deal about this fact. My next favorite example to do is, let's do something like integral from minus infinity to infinity of 1 over x to the 4th plus 1. That's a nasty little integral to try to calculate using freshman calculus. Best way to do it would be to do it, well, you know complex analysis now, so I could do partial fractions and have a good time doing it. But the residue theorem makes it just pop right out. And so when I do my big D, here's 0, here's minus r plus r, counterclockwise, I'd have my C sub r and my L again. But now this is the f of z would be z to the 4th plus 1. 1 over z to the 4th plus 1. The book factors 1 over z to the 4th plus 1, and it gets kind of ugly in my opinion. The zeros of z to the 4th plus 1 are e to the I pi over 4, e to the I 3 pi over 4, and there's two more, e to the I 5 pi over 4. Those are outside the d, so they're not going to contribute. This one's e to the I 7 pi over 4. I use the denominator estimate and see that the integral around the circular part goes to 0, and these, so my integral along the L of my f of z dz plus the integral around my circular part, the denominator estimate there shows me that goes to 0, and that's going to be 2 pi I times the sum of the residues. So that would be the residue at e to the I pi over 4, which is square root of 2 over 2 plus I times the square root of 2 over 2 of my f, plus the residue, let's see, that one's minus the square root of 2 over 2 plus I times the square root of 2 over 2 f. This one goes to the integral we want. So let's see, it's typical when you do these problems to call the integral you want I. This one goes to I. This one goes to 0. And let's see, I got to think about what those residues are. I've got 1 over z to the 4th plus 1. I'll call that f of z over g of z. Where, of course, f of z is the function 1. And g of z is z to the 4th plus 1. Let's see. Of course, g is 0 at one of its roots there, so g of e to the I pi over 4 is 0. And what's g prime? G prime of z is 4z cubed. And so g prime of e to the I pi over 4 is 4 e to the I pi over 4 cubed. That's equal to 4 e to the I 3 pi over 4. And so the residue at e to the I pi over 4, using that formula, is f at e to the I pi over 4, which is 1, divided by g prime at e to the I pi over 4. That's 4 e to the I 3 pi over 4. And so I get 1/4 e to the minus I 3 pi over 4. What's that? Oh, that's an easy thing to calculate. That's equal to 1/4, let's see, that's the square root of 2 over 2 minus the square root of 2 over 2i. Okay, what do you... Yeah, that's what it is. And then you can do the same. I won't do it because I'm running out of time. But at the other spot, e to the I 3 pi over 4 of 1 over z to the 4th plus 1 would be equal to 1 on the top, and then you'd get 4 times e to the I 3 pi over 4 cubed, which would be 1/4 e to the minus, let's see, what is that? That'd be e to the minus I 9 pi over 4. And I could figure out what that is. That's equal to 1/4 square root of 2 over 2 minus I times the square root of 2 over 2. And so in the answer is going to be that my integral from minus infinity to infinity of 1 over x to the 4th plus 1 dx is equal to 2 pi I times the sum of those two things. So that's going to be 2 pi I times 1/4. When you add those two things up, what happens? The real parts cancel, and I'm left with minus I times 2 times the square root of 2 over 2. And that simplifies to the real number you expect. It's got to be a real number. Something like that. Question?
For the contour that you draw, because it like affects which poles that you use.
Right.
How do you? Because I know it's kind of arbitrary.
Well, it's natural to pick this one first. I could have made the bottom D going clockwise, and then I'd get different poles, but I'd get the same answer. And I'd have to use the negative term in the residue because it'd be clockwise instead of counterclockwise.
But it always comes out to the same answer.
Yeah, the answer's the same because it's correct either way you do it. In the other one, it was critical I choose the top because of the boundedness of e to the ISZ in the upper half plane. And that's what, and so I couldn't say either or. But this one could go either or. Question?
Well, no, it's just a general. For the previous case, how do we know it's bounded in the upper half plane?
Oh, well, I calculated that. I did an estimate